Today I want to look at the fundamental theorem of algebra. And we're going to use this, and we're also going to look at how to find equations of functions. But the fundamental theorem of algebra says that in the complex number system, every nth degree polynomial function has precisely n zeros. Okay? Now, that's the complex number system. We talked about earlier, we found ones where in the real numbers, we got a certain number of zeros that translated into x-intercepts. And we didn't necessarily always have the same number of zeros as we had x-intercepts. Okay? For example, you might have had a quadratic that looked like this, where typically we would have, 2 zeros, but in this case we don't have any, because if you solve it for where that function equals 0, you end up getting imaginary numbers or complex numbers. Okay? But the fundamental theorem of algebra, you can see here in kind of a formal statement, says if f of x is a polynomial of degree n, where n is greater than 0, then f has at least one zero in the complex number system. Okay? And to specify even further, you have what I have written up at the top. Okay? It'll actually have exactly n zeros if you count multiplicity. Okay, so for example, if I were to set this function here, x to the 7th minus 3x to the 5th equal to 0, all right, how would I solve this? What?
X to the 6 times x minus 3.
Okay. In order to get it to be, this is x to the 5th here.
Sorry.
We do need to factor. Let's check how we would factor. We're going to factor out x to the 5th. And what would be left over? X squared minus 3. If there's still an x with the 3, we didn't factor out enough of them, right? So we have x squared minus 3. So now we got to keep going here. So x to the 5th, and do you guys know how to factor x squared minus 3?
X plus 2x.
Not. No.
How do you say that? Square root of 3 to the square root of 3 squared plus x times x x minus 2 root of 3.
There we go. X plus the square root of 3 and x minus the square root of 3. Okay? If I asked you to factor x squared minus 9, what would you factor that into?
X plus 3 minus 5.
Yeah. Where'd the 3's come from?
To 9.
You square rooted the 9, right? Well, just because it doesn't happen to be a perfect square doesn't mean you couldn't apply the same principle here. Okay? Now there are other ways you could do this, but I just figured I'd show that to you. Okay? Back in Algebra 1, you guys learned how to factor the difference of squares, but you always did it when there were two perfect squares. We can adapt that same strategy even when they're not perfect squares. Okay? So, here though, we look at our zeros. Okay? Our zeros in this case are going to be where? X equals 0. Good. We have the negative square root of 3 and we have the positive square root of 3. Alright? But how many zeros should we have? Total.
5.
Okay, what has a multiplicity of 5? The 0, okay? This has a multiplicity of 5 because x was to the 5th power, right? Now this makes sense because if you look at our fundamental theorem of algebra up here, we should have how many zeros in this equation? Good, Matthew, we should have 7. Our degree here is 7. Okay, so we should have 7 zeros. We have 7 zeros, it's just that 5 of them happen to equal the same thing. They happen to equal 0. Alright, so we can actually sketch this function. We put a 0 at 0. Radical 3 is about 1.7. Okay, you could just put radical 3 and minus radical 3 on here. Okay, what's this function doing as we go to the right? It's going up. So that means that to the left, what's happening? It's doing the opposite because we've got an odd degree, right? So it's going to go down. Now watch this. This multiplicity 5 means that we're not just going to go straight through the 0. We're actually going to level off quite a bit and then go through it. Okay? That's something like what that would look like. It's an odd multiplicity, so it does still pass through the x-axis at that point. Okay? But it's going to level out a little bit before we get to that point. Okay?
So do the zeros.
At the 0, it levels off a bit because we have that multiplicity of 5. All right, so that's our fundamental theorem of algebra. It tells us how many answers we should be getting here. And when you're doing this, this is a good way to catch yourself if you forget to state the multiplicity. Make sure you've got all the zeros accounted for. I was supposed to have 7. If I forget the multiplicity, I've only got 3. So we got to make sure all of our zeros are accounted for. Okay? Alright, so real quickly here, let's think this through. If we have a polynomial of degree n, you can factor this into that many linear factors. Okay, we've done a little bit of this as we've done the rational zero test. Okay, and from those we can find the zeros. Okay, so 2x plus 1 equals 0. If you've got let's say we have a function here, and it's factored into 2x plus 1 times 3x minus 5 times x squared plus 25. Okay? Now, have we done what this says we can do yet? What's the degree of this polynomial? 4. So how many linear factors should we be able to factor it into? 4. We have this one that's a quadratic factor. Okay? So there should be 2 other ones. So let's actually look at...
Wait, what do you mean there should be 2 other ones?
Well, this x squared plus 25 should produce 2 different linear factors.
The plus and minus.
Okay?
Why are you living it all together, not separated?
Well, I have them separated because of what I want to look at here in a second. This is how we're going to figure out what these are, okay? When you're thinking about zeros, we factor it so that you can look at each factor separately, right? Okay? So, when you see the 2x plus 1, you're thinking, okay, what would make 2x plus 1 equal 0? Right? Well, what value of x makes 2x plus 1 equal 0? Negative 1 half. Okay? Negative 1 over 2. How about the 3x minus 5? Good, 5/3. Positive 5 over 3. It's always the opposite of the constant over the coefficient. Alright? But we've got this x squared plus 25 equals 0. Close.
Positive 5, positive 5.
If it were x squared minus 25, that would work.
Positive 5, positive 5.
Well, we don't know if the 5 is positive and they're both negative.
Well, let's think about this. What did we just learn about yesterday?
Can you do the perfect square thing?
Could we do the perfect square thing?
Yes.
No, because you don't know if they're both positive.
Well, you
Well-
know x squared and then 25 are positives, and they're both perfect squares.
Hang on, what were you?
No, because it has to have negative, or it has to be minus.
Okay, hang on. Did you guys hear what Rachel just said? Say it again real quick.
It has to be like x squared minus 25.
Okay, it has to be x squared minus something to do that, right? Could we make this x squared minus something?
Minus negative 25.
What'd you say?
Minus negative 25.
X squared minus a negative 25. How did we factor it when we had the difference of squares?
Imaginary number.
We will have imaginary numbers here.
Minus 5.
What did we put in the two, what did we do with this number when we factored by difference of squares?
Square root of 95.
Square root. We had the square root of negative 25, which equals what? 5i. So it'd be x plus 5i, x minus 5i.
Please stop.
Wait,
All
Can
right?
we just choose one?
can you show the step with the
No, you gotta have both of them.
Can you, so after the x squared minus the negative 25, that's x squared minus square root 25 and x squared.
This would be the same as x plus the square root of negative 25, x minus the square root of negative 25.
How could you do the minus though? Isn't the minus positive?
Well, no, because this minus is in the radical. This minus here is in the radical. Or are you talking about this minus minus?
Yeah, that minus minus.
Well, yeah, that equals positive 25, but I'm rewriting it so that I can factor by difference of squares. I had to make it equal the same thing. So minus a negative is the same as x squared plus 25.
Yeah, but then how can you do the x plus square root of negative 25?
Well, because think back to how we factor by difference of squares. X squared minus 9, you square root the x and you put that in both.
The middle has to cancel out.
And you do plus and minus, and then you do the square root of 9, which is 3, and the square root of 9, which is 3. Okay? We're just adapting something you guys learned. Whoa.
So if it's positive, it has to be the negative, the x minus the negative.
Yeah, if you had an x squared plus something, you would have to rewrite it. Okay? And guys, this is where what we were doing with the complex numbers yesterday carries over into stuff that you learned back in Algebra 1 and even Algebra 2. Okay? So, this actually shows us now we can write this as the product of 4 linear factors because the degree is 4. The last two would be x plus 5i and x minus 5i. And this also will tell us what our last two zeros are. What are our last two zeros? X equals Yeah, plus or minus 5I. Okay?
You can't graph imaginary numbers, can you?
Not on our XY plane. There's a different coordinate plane that we have for imaginary numbers, but we're not going to mess with those right now.
Right now.
Okay? We tie it together later on in the year when we look at vectors, but that's it. Okay? So notice here we got all 4 of our zeros, even though 2 of them were imaginary and we wouldn't be able to graph them. Okay, we got 4, and we also got 4 linear factors. Now that's important. The reason why I spent so much time with this is because of the following, alright? Alright, so applying that here, we can find all the zeros. This is kind of a start to finish. We kind of just did one where it was already broken down for us. Here's one where we're given a function x cubed plus 4x, and we want to find all of the zeros for it. Okay? So, what do we do first? Factor out an x. Good. F of x is x times x squared plus 4. Okay? So I already know one of our zeros. X equals 0. Okay? So, how would we handle that x squared plus 4?
X minus x squared plus 2.
Okay? You can see that as x squared minus a negative 4. So that would then factor into what?
X minus 4i.
X minus 2i. There we go. X minus 2i and x plus 2i. The square root of negative 4 is 2i, so that's what that's going to factor into. Alright, so our last 2 zeros are plus or minus 2i. Okay? And you see here, I have this term complex conjugates. The cool thing about this is that if you have, okay, if you have a plus bi, or something that has an imaginary part, notice down here, it says if you have a plus bi, where b does not equal 0, and that is a 0 of the function, then the conjugate a minus bi is also a 0 of the function. Every time. Okay? So here's something. If I told you that we had a 0 at 3 minus 2i, you would automatically know what?
3 plus 2i will also be 0.
Yeah, you would know that 3 plus 2i has to be a 0 automatically. Okay? This only applies when you have a complex number that has an imaginary part. Okay? If I had 5 plus 4i root 3, what else would I know?
5 minus 4i.
Yeah, I would also know that that's a 0. Okay? So these always come in pairs like this. The complex conjugates will always be zeros in pairs. Okay? Alright, now, how can we use this? Alright? How can we use this? We're going to write a function. A lot of the times, we actually know what the zeros are. Okay? You're coming up with a situation, you might know what values will give you a 0, but you want to come up with a function to represent that. You also might know one point that would fall on this function. Okay? Now, let's think through this here for a second and look at this example. It says, find the function of degree 4 that goes through the point 2, 8 and has zeros at x equals -2, 3, and 4i.
X plus 6.
Would it also be what?
Negative 4i.
Okay. Why do we know that? Okay. The complex conjugate. Also, there's something else in the problem that should have kind of made us be thinking a little bit here. Very good. I said it was a degree 4 polynomial, and I only gave you 3 zeros. Okay? So automatically know something's wrong here. We're missing something. We're missing that 4th zero. Okay? Now, here's the fact of the matter. There are an infinite number of functions that have those 4 zeros. So, that's why we have a specific point that we wanted to hit. There's only one of those that will hit the point 2, 8. Okay? So let's look at how we would find this. First of all, we start writing our function, and let's write it with those linear factors. Since we know all of the zeros, we can now figure out what the linear factors are. Alright, so what's one linear factor?
X plus 2.
Very good, x plus 2. Alright, because -2 is a 0. What's another linear factor? X minus 3, very good. And another one?
X squared plus 6 plus.
That's right, okay. We would have, you could make it x minus 4i, and then x plus 4i. If you FOIL that together, you will get x squared plus 16. That's great. Okay? So let's actually write that. F of x equals x plus 2 times x minus 3 times x squared plus 16. Okay? Now, if you plug in 2, do you get 8? Let's see. 4 times -1 times 20. Does that equal 8? No, that's a problem, right? Okay. Well, here's how we solve that problem. Remember, I told you there were an infinite number of possibilities of functions that have those 4 zeros. What will change all of the points on the graph except for where the zeros are is my leading coefficient.
Could you say that again?
Huh?
Could you say that again?
The leading coefficient will change all the other values, because notice that's going to stretch or shrink this vertically, right? Think about our transformations. A will stretch or shrink it vertically, but the zeros are on the x-axis. So no matter what I multiply it by, 0 times anything will still be 0. So it won't affect my zeros. Okay? So, we've got to figure out the A that will give us, that will make this function hit the point 2, 8. So how would we do that? Any ideas? We don't actually have to FOIL.
Just plugging them.
I want my function to hit the point 2, 8. So I've got to find the one value of A that's going to make that happen.
Maybe synthetic.
Wait, what?
Plug in 0.
Plug in 2 for,
And that.
not for A,
X.
for X,
And then 8 for A.
and 8 for
X.
f of x, okay? So listen, this right here is telling us, oh, my pen's dying. okay? This right here, this point here is telling us that f of 2 equals 8. Alright, so we are going to take 2 and we're going to put it in the place of x. Let's do this in purple. Okay? So there's a 2 there, a 2 there, and a 2 that's being squared. And we're going to put an 8 and we're going to plug that in for f of x. Okay? And we need to solve for a. Alright? So, we get 8 equals a times 4 times negative 1 times 20, which happens to be a negative 80. So we have negative 80a equals 8. That means a is a negative 1/10. So now I know my function is f of x equals a negative 1/10 times x plus 2 times x minus 3 times x squared plus 16. And now I have a function that has all 4 zeros that I'm looking for. The degree is 4, and it's going to hit the point 2, 8. Okay?